Today we're going to be talking really about a pretty straightforward example of Tensorflow, and this example actually comes from the Tensorflow documentation, which is really quite nice because it means that there's lots of other people who've worked on it, there's lots of good examples, and there should be lots of tutorials you can follow for every bit and bob. What I really want to focus on today is just walking through this code so you get a sense of how it works, roughly what the flow is. We'll talk about in later lectures all kinds of other aspects of it, but for the moment we're just doing, again, these high-level overviews for sort of orientation. So the first piece we see, as always in our Python files, we're going to be importing our libraries at the top. Again, we're bringing the TensorFlow library as TF. That's almost like a naming convention, and this allows us to refer to everything that's in this TensorFlow library as TF dot whatever else it is. We'll be using the Matplotlib library, which if you haven't used, is a wonderful library for making pretty simple plots. There's lots of fantastic things you can do with it, but I will be honest with you, I only really use Matplotlib for the simplest functionality. And what we're going to do is we're going to actually use that TF dot, and we're going to pull in from Keras, which is a wrapper on TensorFlow, the datasets file. So we're going to pull in this object that already has the MNIST dataset. And this is one of the advantages of working on something like Colab, is that Colab maintains this small amount of RAM and disk, and we can import this library in a standard way. I like it for toy examples. It lets you see what's happening. Pretty straightforward. And we can pull in this data, and we're going to unpack the data into its 4 components. So when you're using TensorFlow's datasets, very often you'll have xtrain, ytrain, you'll have xtest, and ytest. Each of these values will give you a good way of understanding. It's these standard datasets where you have your training data and your testing data, and it's split. It's just very convenient for bringing these pieces in. And then what we're going to need to do is we're going to convert our xtrain and our xtest, that's the stuff that we're going to be working with in this MNIST dataset, into components. We'll be taking and normalizing over the value of 255. So we'll be getting a percentage. So where we started with integers between 0 and 255, now we're going to end up with values between 0 and 1. Now, the first thing that I'd be wondering if I were in your shoes is, this is all great, but where do we start? What's the very beginning? The very beginning is we're working with a set of problems, and what I want to do is plot what this stuff looks like. So we're going to make a new code block, and we're going to move that code block up to the top. We're going to bring that code block in, exactly the same code that's here, and what I really want is to preview and visualize this data. So we'll remove our comments, and then we'll execute this code, and what we see is that when we look at the first example of xtrain, it's the number 5. It's a handwritten digit, and if you are familiar with the MNIST, you'd know this instantly. These are handwritten digits of the values of 0 to 9. And what we have is a whole collection of them. And you see that they're all very different. They don't correspond with the numbers. We could choose a value. And you can see that the 100th value looks like a 5. It looks sort of like my handwriting, what a 5 might look like. We're using Matplotlib's MatShow to be able to get a hold of this. The next thing that I would wonder if I were in your situation is, well, that's all well and good, but how many of these do we have? So I might do xtrain.shape and plot that just to see what the value is. And we can see that it's 60,000 examples that are 28 pixels by 28 pixels. So our images that we're working with is a 28 by 28 grid, and all of our digits have been written within that space. We have 60,000 examples in our training. In our test, we have roughly 10,000. So we're looking at a total of 70,000 total examples. Now, we're not going to again talk too much about this. You can read all about MNIST online. It's very well understood. We're going to get right into the heart of our deep learning example. So the first thing we often have to do when we're training a deep learning model, really regardless of the library that we're using, is we have to think about the shape of the data first as it comes in, and then we're going to think about it as it comes out. Of course, we're trying to label digits between 0 and 9, so the shape of it's coming out. We know that it's going to have to be a value between 1 and 10, and the easiest way to do that is to have 10 layers down at the bottom. But what we're going to do here is we're going to start with the input shape. So we'll bring it in that 28 by 28 grid, and we're going to convert it down into one of 10 values. That's 0 through 9 in terms of our output. So what we will do is we'll start with this TensorFlow Keras models sequential. Sequentials are the plain vanilla neural networks. They're the simplest to get up and running. And this is a pretty standard model for writing these. We're going to set up a model. We're going to define a model as through the function for sequential. And now what we're going to do is we're going to pass it a structure. This is our neural net structure. Our structure has a sequence of 1, 2, 3, 4 layers. The first layer flattens the object. It brings the object in as an input shape. Then we're going to take our second layer, we'll take a dense object of 128 values, and it will run a ReLU activation. We're not going to talk about what the activations mean. For the moment, we're just going to do this. We then will have a layer of dropout, and then we'll have a layer of a dense where we project back to those 10 dimensions. So we start with that 28 by 28 square, we flatten it, we compress it down to 128 values, then we move it once more, again down to 10 values. Now to do this, we're going to use a loss function. How do we know when we're in the right area? We're going to use a loss function that's called Sparse, Categorical, Cross Entropy. It's a mouthful. For the moment, again, we're not going to talk about the specifics of this. I just want to get through the mechanisms of how this code is going to run. We have to define this as logits equals true. And all we do then to execute our code is all of this definition. None at this point in time, no code has run, no code is really executed. It's all been setting things up. Our model has been defined, and there's been space allocated for it. That's a little bit of a questionable statement in space allocated. We've defined the symbolic graph for which this code is going to execute. But we haven't run anything. So if you had a model that was needed to run 10 or 15 hours, these functions that we've put up on the screen so far that are highlighted, those aren't going to take 10 or 15 hours. That should happen in seconds. This compiling process will set aside, will really define that graph and fix it so that it's in memory and ready to take data. So if you think of this as a model definition, we think about this as really getting that symbolic graph organized and ready to go. But again, we haven't run any data through it. And to do this, we have to have an optimizer. Again, we're using Atom. We need a loss function, which is what we just defined here. And we need some metric for estimating whether or not we're doing a good job, and we'll use that as accuracy. You could use different metrics here. There are different options and all kinds of different things you can change. For our purposes right now, we're not too worried about it. We're just going to let this run through. Again, at this stage of the game, no data has run through the model. Now, the first time data starts to run through the model is when we call model.fit. And in this case, we're going to pass all of the training data, both of the X and Y, and we're going to run through it 5 times. All right, so we'll have 5 epochs. And then we'll run a model evaluate with the X test and the Y test. So we've trained on one set of data, and we're testing on another set. Now we sort of take for granted in all the investigation that we've done so far that there are no duplicate examples from XTrain and to XTest. But since this is a standard library, that's a pretty safe assumption. And if we click this, what we'll see is we get the spinning wheel as things start to run. We see that there's a ticker bar that tells us how long the model's running. Expand this a little bit. We see that our accuracy moves up to a value of 0.9, and we go to 9.5, 9.6, 9.7. And you can see that it keeps increasing. We have a loss, which is how far away we are from the optimal, sort of where we want to be. Our loss keeps going down. So our loss decreases, our accuracy increases. And now what we'd like to do is to test our evaluate. And you notice here we have a verbose equal to 2. This is really, this is how we're understanding how well our models actually, verbose is a tool that allows you to see the outputs so you can see what's actually being printed rather than being held off. And you can see here our values are coming through the evaluation, which is our loss function, which is this 0.74, our accuracy, which is 0.976. Again, what's important for us is our model isn't overfit. That is, our loss looks vaguely pretty much the same as what it was in the train and test. That's a good sign. And our accuracy looks very similar from train and test, and that's a good sign. Now, this little bebop of code, right, it's not too much. It does, however, have all the components that are necessary to understand how deep learning works. This is a feed-forward network, and one of the things you'll note is that a lot of the more complicated networks that are the most exciting today have a more complicated architecture. But these are the guts. This is what we got excited about in 2015, 2016. Just being able to do this was considered a great engineering feat, what we got through in a little over 5 minutes. Today, it's not nearly as exciting as it once was, but it's the foundation for everything that we're going to work on. So as you are learning of these pieces, what I've also done is I've added sort of a glossary down below that lists all the different things you should go and look up and get a sense of what these words mean, and great questions to ask yourself, sort of a knowledge check. I'm sure I've missed a couple. Probably could have added Matplotlib at the bottom. But what I want to focus on more than anything is this flow structure, the way this code is working. The code is bringing some data, so we prep it up so that we're ready. We have one section where we define the model and we assign some values, hyperparameters. This is the values 128, a ReLU, a dropout. We could change the structure. In fact, let's do this. I haven't done this before, so let's see. what this generates, we're going to make a second layer of 128, again with dropout, before we classify all the way down. And let's see how our model performs. Our model's started again from the beginning because we removed the space and we're running this value again. Our loss is 0.29. Our accuracy is 91. Our loss goes down. Our loss is continuing to drop. Our accuracy is continuing to rise. Our loss is continuing to go down. Our accuracy is continuing to rise. We're in roughly the same zone. We're coming up on the fifth value. We were at a 97 the last time, and we're getting pretty close. Notice our model's still running. Now it has to run the 10,000 examples all the way through. We just have to wait for a moment for it to finish. And we'll see if our more complicated model, that is with 2 layers, in fact is correct. And it looks largely the same. I'm not super excited about that. So, I've heard that training deeper and deeper models is in fact better. So if we just keep doing this, do we think our model will get better? I'm not sure. Let's give it a go. Again, I haven't tried this yet, so let's see what's going to happen. Notice it's taking a little bit longer for our model to run. We have a deeper network structure, which requires more learning. Our accuracy is in fact lower. Our loss is significantly higher. It's not too surprising though, right? Because we started with a much more complicated neural structure, lots of random values that have to be learned. This isn't too far off. We're at 94. I believe the last time we were at 95. Now we see the 95. We're up to 96. Now let's see where we make it to. We didn't make it to 97. So I'm not even going to continue. I'm just going to stop this. Runtime. Oops. Continue. There we are. Let's continue. I think maybe we should try some more epochs because who knows if that's the right number. Let's run 10 epochs rather than 5. And it looks like we're going to still be under 0.90. We're still hovering in that 94, which is basically what we expected. We wouldn't expect these numbers to be too dramatically different because we're starting again from the beginning. What's going to get interesting is when we get up to these 95 of the epoch 6 and 7. So we're still hovering in the 9.6. This is pretty close, but I think we were at 9.7. Now, are we going to cross over? We do cross over, but we're struggling. We're right at that borderline. We're going to move forward. We're creeping forward, but just a bit. A little bit more. Now what we're going to see is that despite adding a tremendously larger number of set of parameters, right, our model hasn't done much better. We were able to do with 1 layer what we've just done, another 4, and we didn't really see an increase in accuracy. If we wait for this whole thing to finish, we will see how well our model's doing. And again, our model has a loss that's roughly the same, roughly what we might expect, and our loss is similar to our accuracy here, so that's a good sign. We haven't dramatically overfit the model, but we haven't gained a lot. Our runtime's a lot slower. It takes 7 seconds. I think we might have started at 3 seconds per epoch for no noticeable increase in accuracy. And if you liked that process, what we just went through of tinkering with these different values, if you think that's fun, then deep learning is really for you. That's what you're going to spend a lot of time doing if you get excited about twiddling the values of your network. The other approach that you can take to deep learning engineering is changing dramatically the architecture. So here what we've done is just change some of the hyperparameters in a very sort of vanilla feed-forward network. You can get into all kinds of more complicated things with different structures. We're not touching on any of that today. Today, I just want you to focus on this rough outline. Take this TensorFlow example in Colab, get it up and running, see if you can play with it, try some different values, try and look at some of the other data sets that exist in this Keras tool. Look for something that can run on Colab so it's small enough that it doesn't take up too much of your RAM or disk space. I don't think many of them should, but I haven't played with them all. Go get some experience there and then let us know how that works for you. I hope this has been helpful. My hope is to keep creating a few more of these that are very simple and directed and really point out the foundational pieces. I'd like to show you another example very soon that looks not with TensorFlow, but with PyTorch, So you can see similarities and differences. I think that's really quite useful. It doesn't really matter which language you start with or which library you start to do your deep learning in. Largely, once everything's all taken care of, you'll be able to move between the two. There are differences, but it's not as extreme and not something you should worry about right now. But it's helpful to see at least 2 examples so you understand some similarities and differences. Anyway, hope this was helpful. Look forward to talking again soon. Thanks.